Today we're going to talk about inductance and inductive reactance in series and in parallel circuits. The nice part about inductors and why we start with inductors when we start AC theory is because we treat them a lot like we treat resistors. We understand they're going to take voltage and current out of phase with each other, but when we're doing our calculations for the circuit, they're treated a lot like resistors are, say, in DC theory. And we can see that with our formulas here. In a series circuit, like the one we see to the right, if I wanted to know what the total inductance of that series circuit is, what I would do is L total inductance, is equal to inductor 1 in Henries plus inductor 2 in Henries plus inductor 3 in Henries, and so on. So we can add up all the Henries to get a total Henry value. But Henries don't help us make calculations for current or voltage drop, like we know happens in a series circuit. So we have to convert Henries into something we can use, which is ohms. And if you want a better explanation between inductance and inductive reactance, you can view one of the older videos on this page. But we'll look at that process a little later. The other thing I can do, because we do have those two forms of measurement, one in Henries tells me inductance. The other one is inductive reactance, which we measure in ohms. That we also can add up in series, just like we added up resistance ohmic values in series. So we can take inductive reactance of L1, the inductive reactance of L2, and the inductive reactance of L3, and add them up to get our total. So if we take a look at the circuit here, we have a series circuit. We see our coils are all in series. Current has no other path. So we're going to add them up. We have a 2 Henry inductor here for L1, a 1 Henry inductor here for L2, and a half a Henry inductor here for L3. You're like, half a Henry? How's that happen? Well, the funny bit is inductors are actually pretty small when we measure them in Henries. A lot of the time we're going to be dealing with millihenries, not even full Henries. So having a half a Henry is still pretty large. So if we add all those up, we will get 3.5 Henries. And that is the total inductance for this circuit. But now I want to know which one of them is going to drop the most voltage. Now I want to know how much current is going to apply to this circuit. What's the draw? So I have to convert them into ohms. Well, we got X of L1 here, 753.6 ohm. X of L2. We have to call it something else because we can't call it Henries anymore. We converted it. X of L2, 376.8 ohm. And then X of L3, 188.4 ohms. So now we can get a total ohmic value for this series theoretical inductive circuit. We take 753.6, we add 376.8, and we add 188.4, and we find that we have 1,318.8 ohms of opposition in this circuit. Here's the fun part. we can also double check our work. We calculated it in henries. We calculated it in inductive reactance, but let's prove we're right. And this is where we'll see that X of L formula, 2 pi for life, 2 pi times the frequency of the circuit times L, the Henry. And you might be sitting there going, well, I don't know what the frequency of this circuit is. I have no idea what the frequency of this circuit is. But we can find out because we have the ohmic value and we have the henries. That means we're going to take our nice little inductive reactance formula here and rearrange it. I want to solve for frequency here. And this is all multiplication. So what I'm going to do is I'm going to divide out 2 pi L. And that'll cancel out 2 pi and L. And what I do to one side of the equation, I have to do to the other. So I have X of L over 2 pi L now. That will equal our frequency. So let's test it out, right? We have X of L of our 188.4 ohm inductor of XL3. We're going to divide that by 2 times 3.14. We always use 3.14 for pi. And the value in henries, 0.5. So I'm going to take 188.4, divide that by parentheses, 2 times 3.14 times 0.5, hit the equal sign, and what I get is our frequency here of 60 hertz. Most common frequency in North America, 60 hertz. So now we've proven forward and backwards our numbers are good. So I have 60 hertz now. I know we're operating this circuit at 60 hertz. I can double check my total versus my inductive reactance total. I can take our inductive reactance formula, 2 times 3.14 times 60, which we just calculated, times 3.5, and look at that, 1,318.8. So let's start to take a look now at parallel circuits. And you'll remember from DC theory, we don't add resistances up in parallel because as we add branches, we reduce total resistance. It's the reciprocal method. The same is true when we talk about inductors. So L total inductance in parallel will be the reciprocal method. 1 divided by 1 over L1 plus 1 over L2 plus 1 over L3. And the beauty of inductors is no matter if we're solving for inductance or inductive reactance, we treat them the same. X of L total will equal 1 divided by 1 over X of L1 plus 1 over X of L2 plus 1 over X of L3. I hope you find this to be helpful. If there's anything we can do to clarify anything for you, please leave it in the comments below, and have a great day.